A good session. Thanks for that, Dan. And I'll be the speaker for the last session where I'll be talking about the relevance of classical algorithms in modern autonomous driving architectures. My name is Prajwal, and I'm currently working as a lead algorithm development developer for AppDev. And if you don't know AppDev, it is basically an automotive company. It used to be part of GM earlier, became Delphi, and then it became AppDev. We do a lot of autonomous driving as well as driving assist and parking solutions for top OEMs all around the globe. And I am specifically working in mostly the parking part of the company where I develop algorithms for autonomous parking, be it planning or control, or even in some cases related to perception. Okay, moving on. Let's quickly go into the introduction here. In this talk, I want to talk about basically how the autonomous driving world is evolving in terms of what kind of methods we are using to do the end-to-end autonomous driving. And when I say end-to-end, it involves three things, right? It involves perception, it involves planning, and it also involves the control. And so whatever I'm currently going to talk about is also going to apply to any robotic system. Those are the three different components of any robotic system, autonomous robotic system. And it's the same even in like autonomous driving. So these can be applied back and forth. So right now, what we are seeing in today's world is that like we are trying to uh, heavily rely on learning-based algorithms, specifically for doing autonomous driving and completely from end-to-end control, right? So you take a raw video image and then a raw video and then feed it into an AI model or a deep or a learning model, and then it basically comes out with a motion controller command. So it basically gives you an output on what needs to be the actuator command to handle that specific scenario that are recorded by the sensors. So that's basically the end-to-end aspect of it. So we are not just doing, for example, image recognition or detecting the lanes or detecting the VRUs, for example. It's we are also including the planning as well as the control component in machine learning, and this sort of methodology has been already adopted by many OEMs, and many more OEMs are actually developing these kinds of methodologies where they are completely relying on end-to-end ML. And Traditionally, when you look at any autonomous systems, they involved a lot of classical algorithms. When I talk about classical algorithms, they are mostly in terms of planning and controls. So these are the systems, or these are the subcomponents within autonomous systems that have traditionally been classical algorithms, and they are continuing to be replaced by learning-based algorithms. But now these planning and control algorithms or rather classical algorithms are completely different in the way they operate in terms of reliability, in terms of interpretability, and in their nature of how deterministic they are as compared to machine learning models. So that's where we are currently thinking about how to integrate both the approaches, because we don't want to lose the advantages that we have with classical algorithms. While machine learning algorithms are more powerful, they can handle more edge case scenarios, and they also in some cases more easier on the compute. We still want to have a certain level of guarantee that is provided by classical algorithms. And how do we integrate both of these approaches is something that I want to specifically talk about in this talk here. So first coming to why classical algorithms still matter. As you all might be knowing that, like, Tesla is kind of doing an end-to-end system where they're even controlling right from the video to the controls. They are completely passing through an ML pipeline, and that basically skips everything that we know about using classical algorithms. But classical algorithms still have a very distinct advantage that they are very predictable. So, for example, if you have any set of outputs, and if you want to create an algorithm that performs in a certain set of limits, you should be able to create that with classical algorithms, because you know the entire dynamics of how they operate. So you should be able to at least like tune these algorithms. For example, if you look at any control algorithm, if you know the driving limits, the range of the actuators, and then what are the different conditions, or what is basically the tracking performance that we need, you should be able to determine that there is a classical algorithm that can be tuned in so and so way. And with this level of observability and controllability, we should be able to control the vehicle to follow a particular trajectory. And that is something that is very important in safety critical applications like autonomous driving. And that's the reason we want to have that aspect as it is while we are using end-to-end ML algorithms, and getting the advantages of using ML algorithms. And the second one is transparency and interpretability. So when I talk about transparency and interpretability, it's basically about how well you can debug with the data that you have. For example, if you have an end-to-end ML network and you are just feeding it raw video and expecting a controller output, and you see that the controller output is really absurd or it's really hallucinating over something, and this sort of a behavior, if you're using classical algorithms in the place of end-to-end ML, you will find that it's very easy to debug classical algorithms, because you will have the entire inner workings of the classical algorithm. So you can basically tune or fine tune your model, physical model that you have used in the classical algorithms, or you can also fine tune like several parameters, or completely change the algorithm by itself to overcome these difficulties. And that's also something that is really important, especially in safety critical applications or safety critical algorithms like control, motion control. And finally, efficiency on embedded systems. So these sorts of classical algorithms that I'll be talking about in the next few slides, they have been tested and have been working for last 2 or 3 decades for cruise control, adaptive cruise control, and things like lane keep assist. So these are all already running, and they're all already in production, and that too on a very low compute device. So in any like normal, or not the highest trim level cars, if you take any of the lower trim level cars, they all come standard right now. Features like lane keep assist, features like adaptive cruise control, they all come standard at that price point, just because of the lack of need for a heavy compute. And that can only be realized when you're using say a simple classical model that can handle very low compute requirements. So here I'll just talk about classical algorithms that are typically used. The first one is Kalman filtering for localization, and this is a very widely used algorithm. It basically combines data from two sensors, and specifically in localization, it basically combines dead reckoning with a ground truth sensor like a GPS sensor, or even like RTK GPS, to provide very fine-tuned localization for our car. And with that localization, you'll be able to propagate the model forward, and then try to predict how the controller behaves. Next is the path planning, which is basically a path planning algorithm that computes the shortest deterministic path in structured environments. And this A-star path planning is heavily used in parking applications. So, for example, you have a first initial point and a final goal that you want to achieve. And on the way, you have some obstacles that are realized through our perception. You should be able to design a star algorithm that basically plans the entire path, including gear changes, like complete end-to-end steering movements, such that it basically takes the car from the initial location and parks it exactly in the slot or in the parking slot determined by the perception. The third one is the control part of it. Like control is um, pretty much like a lot of the autonomous driving industry uses either PID or MPC controls. They have been like the mainstream control algorithms for a while now, and they are very reliable. And along with being reliable, they also come with a really good level of predictability. So, for example, uh, if you want to, if you are the host vehicle is an evasive maneuver, you actually know the limit at which the car can move, the limit at which the car can respond to an obstacle on the road. Just because MPC controllers are, you can easily resim MPC controllers and understand the level of controllability that you have in the car based on your actuator limits, based on the delays in the system, things like that. You should be easily able to set these controllability limits and operate within that controllability limits. And the final one is SLAM, which stands for simultaneous localization and mapping. This is widely used in mobile robotics, especially with LiDAR sensors, or also even like depth cameras. So with SLAM, it's very easy to understand the exact location within an environment, ecolocation within an environment, and then also to map the entire environment around the host vehicle. So now, how do we integrate with learning-based methods, and how do we take these advantages from the classical methods and implement this in, for example, say an end-to-end learning-based method that's used in autonomous driving systems? So one thing that comes to every OEM's mind is that if I'm using an end-to-end ML based system that does autonomous driving, what is the guarantee that it will perform to a certain set of standards, and what is the guarantee that it will not hallucinate and give some absurd outputs to the actuators that puts passengers at risk. So that's something that can be kind of avoided, or can be kind of like alleviated by basically taking a simultaneous run of these classical systems. So along with the end-to-end ML system, we can also run classical systems since they are also very low on compute. You can basically run these classical systems, understand what is the output from the system, and then try to reason with the output from the other system, that is the end-to-end ML system. So using this kind of architecture where you're simultaneously running both and trying to understand which one is, say, like if there is a predominantly a lot of difference between these outputs, then it can be understood that like there is something going wrong on the end-to-end ML side of things. So that is one way to integrate both of these. At the same time, this sort of an architecture also uh, gives you the ability to be compliant on specific standards that are used in automotive industries. So that level of guarantee can be brought back by using this kind of architecture. The next one is basically enhancing these classical algorithms by using ML in between them. So basically, if you take a look at like sensor fusion and algorithms, you can basically combine Kalman filters with neural networks, especially in the estimation phase, trying to understand what kind of changes can be done based on the input output relationship, um, using a neural network that will improve the accuracy of sensor data fusion using Kalman filters. And also in things like path planning and maneuvering, along with A star optimization, you can also use or adapt the heuristic that's used in A star algorithm with a neural network based heuristic that can also improve the compute of A star algorithm and even the performance. And thus this is another way to like integrate both neural network as well as uh, classical um, classical based methods. And finally, adaptive control systems. This is another big field that is being explored. Basically, in every control system that we use, there is always kind of like a model of the plant. Or basically, when I say plant, it's basically the physical system that's being controlled here. And the physical system that's being used is often a very simplified version of the actual physical system, and any changes to those or any deviations in the physical system versus the plant model that's used in control system will cause a reduction in performance. And this is where the plant can be adapted to make sure that um, the control system performs uh, pretty much well and tracks the path completely. And this is basically the place where we are trying to use neural networks and try to change the plant parameters or even change the plant model altogether to make sure that the controllers are well tuned at all times so that the tracking performance remains good all the time. And also with advanced mapping techniques such as SLAM, this already has a predominant use of neural networks, especially when using like feature extraction. And this part of the algorithm can be mapped to a neural network where, based on the raw image, you can take out interesting features that can be anchored between two images, and then try to understand how much the vehicle or the ego vehicle has moved, or how much the ego vehicle has rotated, for example. So these are different kinds of ways in which we kind of combine like classical techniques with learning-based algorithms, and make sure that like whatever advantages that we have from the classical algorithms are still realized even while using machine learning or neural networks inside our algorithms. So what are the advantages? Like I said, there is always a real-time performance. So classical algorithms sometimes, I mean, most of the times, classical algorithms are really low on the compute. So even in the case where, there is a failure in terms of getting an output out of end-to-end ML solution, you can always rely on classical algorithms outputs to kind of control the car and keep the autonomous system going. And exactly for that reason, they're also like a good fail-safe mechanism. So, whatever scenario you throw at it, as long as it is within the controllable limits, and as long as you have good observability through all the sensors that are mounted on the ego vehicle, you should be able to guarantee that this kind of algorithm will perform and will provide you the tracking result that you need. And finally, like explainability and trust. So this talks about like basically the debugging nature of classical methods. So you can at any point, if there is a really absurd output from the classical algorithms, you can go back. You can go back and you can go back and simulate what's happening in the classical algorithms, and then try to understand where there is a problem, and you can either retune it or correct the model to make sure that it performs as needed. And finally, hybrid system integration. So these hybrid system integration is not really as easy as just making taking out a part of classical systems and replacing it with a neural network, or even taking out a system part of end-to-end ML and replacing it with some classical systems. Primarily because the way in which neural networks operates is completely different in terms of the inputs as compared to classical algorithms. So for classical algorithms, when you think of inputs, you're thinking about host vehicle characteristics such as speed, yaw rate, things like that. And for an end-to-end ML solution, you are thinking about all the data you can get, right? Like like all the big data that you need to make sure that the algorithm that you are training can learn reasonably well the driving behavior. And that's the reason why it's not easy to just integrate both of these solutions. And that's where I mean like the things that I talked about earlier in the previous slides can help, where we are trying to resimulate everything in a physical or or a virtual world, and trying to use those data to basically train the neural networks and not rely on the limited amount of sensors that we have in a normal car. So challenges and future scope, I think I've mostly talked about that. The challenges are that like it's not so um, easy to integrate both classical and ML pipelines in one set of algorithms. There is definitely a complexity in terms of architecture. You'll need to understand how to basically feed the inputs correctly to both of these solutions. And also in terms of like real-time performance, how do you make sure that you're working with the limited amount of data that you have in the car sensors, and trying to understand how these neural networks can perform. So, and finally, compute requirements. Sometimes, there's always running this classical algorithms as a backup for learning-based methods can also demand more compute, because we are always relying on classical algorithms as a backup. And if, for example, if you want to run both the algorithms simultaneously, that would definitely need more compute as compared to, say, using it as a backup, where if one thing fails, you can go back to the classical algorithms to understand, to get some a normal output out of the system. So that's also another challenge that we have right now, and that's of course something that needs to be solved in the future. Yeah, the key takeaways from this talk are basically that classical algorithms are still useful in today's world, basically in terms of assisting neural networks and ensuring a certain level of guarantee that the algorithm outputs are safe to implement. And there is still no doubt that machine learning will continue to dominate the autonomous driving world with the amount of data that we are collecting on day-to-day basis, with the amount of compute that's being used to learn the data, or learn the behavior from all these data points. There is a good chance that machine learning algorithms will continue to dominate with all the data present. And hybrid architecture future is something that many OEMs are still trying to develop, where they are trying to use both classical methods and ML based methods to understand how there can be some sort of a guarantee and a standard process that can be followed. With that, I end my talk. If